In the vast cosmic expanse, stars are born in nebulae, the universe's stellar nurseries. Imagine a colossal cloud of gas and dust, floating in the seemingly endless expanse of space. This is a nebula, a cosmic nursery where stars are born. Nebulae are rich in hydrogen and helium, the essential elements that fuel the birth of stars. Yet these celestial nurseries are more than just clusters of gas and dust. They are the cradles of the cosmos, where the life cycle of stars begins. Picture the nebula slowly contracting under the relentless pull of gravity. The material within the nebula begins to accumulate, forming a dense core. This is the birth of a protostar, the earliest stage in a star's life. As the protostar continues to gather more and more matter from its surrounding nebula, it grows in size and density. Now imagine the heart of the protostar heating up as it continues to collapse under its own weight. The pressure and temperature at the core rise dramatically, setting the stage for a cosmic spectacle. When the core temperature reaches a staggering 10 million degrees, a process that underpins the life of every star begins: nuclear fusion. In this nuclear furnace, hydrogen atoms collide and fuse together, creating helium. This nuclear fusion releases energy in the form of light and heat, causing the protostar to shine brightly. It is at this pivotal moment that a star is truly born. This newborn star begins to emit wind, a stream of charged particles that pushes back against the surrounding nebula. Over time, the wind clears away the residual gas and dust, leaving the star to shine in all its glory. The star's life ahead is determined by its mass. The more massive the star, the hotter and brighter it burns. Yet, regardless of its size, each star follows a similar path, living out its days in the cosmic theater until it exhausts its nuclear fuel. And just like that, from a humble nebula, a star ignites and begins its life in the cosmos. Once a star is born, it enters a phase of stability known as the main sequence. This is the stage in a star's life where it has settled into a balanced existence, an equilibrium between two powerful forces. Imagine a cosmic tug-of-war. On one side, you have gravity, always trying to pull everything inwards, compressing the star into a point. This relentless force is balanced, however, by the energy produced by nuclear fusion at the star's core. This energy pushes outwards, resisting the inward pull of gravity. This delicate equilibrium between gravity and the pressure from nuclear fusion is what stabilizes a star during its main sequence. Now, the fuel for this nuclear fusion is hydrogen. Stars are basically gigantic celestial pressure cookers, converting hydrogen into helium at their cores through nuclear fusion. This process releases an enormous amount of energy in the form of light and heat, causing the star to shine. Our own sun is currently in this phase of life. It's been converting hydrogen to helium for about 5 billion years now, and is expected to continue doing so for another 5 billion years. That's right, our sun, the source of all our warmth and light, has already lived half its life. But don't be too quick to mourn. This main sequence stage is where stars spend the majority of their lives. It's a period of relative calm and predictability. There's a beautiful constancy in the way the stars in our night sky twinkle, a testament to the billions of years they've spent in the main sequence stage, steadily burning their hydrogen fuel. There's something poetic about it, isn't there? These celestial bodies, burning brightly in the vast darkness of the cosmos, each one a testament to the delicate balance between forces of creation and destruction, between light and darkness, between life and death itself. So, in the serenity of the main sequence, stars shine brightly for billions of years. And in their light, we see the enduring dance of the cosmos, a tale of balance, endurance, and the raw, unending power of the universe itself. After their time in the main sequence, stars undergo dramatic changes, transforming into red giants or white dwarfs. These transformations are a testament to the incredible power and adaptability of the stars. Consider an average-sized star, like our sun. For billions of years, it has been happily fusing hydrogen into helium in its core, releasing energy that lights up our world. But what happens when the hydrogen fuel runs out? The star doesn't just fade away. Instead, it enters a new stage of life, becoming a red giant. In this phase, the star's core contracts while its outer layers expand. The star, once a mere speck in the sky, swells to a size that could swallow the orbits of the inner planets. As the star expands, its surface temperature drops and it takes on a reddish hue, hence the name red giant. But the life of a red giant is not a stable one. The intense pressure and temperature in the core eventually ignite a new round of fusion, this time turning helium into carbon. This process, however, is short-lived. Once the helium is exhausted, the star doesn't have the mass to fuse carbon and heavier elements. Unable to support its own weight, the core contracts further, and the outer layers of the star are expelled into space. What remains is a white dwarf, a hot, dense core about the size of Earth, but with a mass comparable to the Sun. This tiny powerhouse shines with a white-hot intensity, but without any nuclear fuel. It slowly cools and fades over billions of years. So, whether it's an average star like our Sun or a massive star destined for a more explosive fate, each one undergoes its own unique journey. From the main sequence to the red giant phase, and finally, to the quiet white dwarf stage, each star paints a picture of cosmic evolution. From red giant to white dwarf, the star's life is a spectacle of cosmic transformation. The death of a star is a cataclysmic event, resulting in either a supernova or the creation of a black hole. Now let's imagine a star, much larger than our Sun, at the end of its life cycle. These massive stars, in their final moments, go out not with a whimper, but with a colossal bang known as a supernova. A supernova is an explosion of astronomical proportions, so immense that for a brief period, a single star can outshine an entire galaxy. As the star exhausts its nuclear fuel, its core collapses under the force of gravity. This releases an extraordinary amount of energy, causing the outer layers of the star to explode. This explosion sends a shockwave into space, propelling the star's outer layers at incredible speeds, while leaving behind a highly dense object known as a neutron star. But what happens when the star is truly gigantic? With a mass many times that of our Sun, the core's collapse can be so severe that it forms a black hole, a region of space where gravity is so strong that nothing, not even light, can escape its pull. The black hole's event horizon, the point of no return, marks the boundary where the gravitational pull becomes inescapable. The supernova explosion not only marks the death of a star, but also the birth of something new. The energy released in the explosion disperses heavy elements, such as gold, platinum, and uranium, into the cosmos. These elements, forged in the heart of a dying star, are scattered across the universe, seeding interstellar clouds that may, in time, form new stars and planets. So, in a sense, we are all made of stardust. The iron in our blood, the calcium in our bones, and the oxygen we breathe were all once part of a star that exploded in a brilliant supernova. In their death throes, stars illuminate the cosmos, their remains seeding the universe for future generations of stars. From birth in nebulae to their explosive deaths, stars undergo a fascinating life cycle. A star's journey begins in the Cosmic Nursery, where dense clouds of gas and dust collapse under gravity, igniting a nuclear furnace that sparks a star into existence. This is the birth. The star then embarks on its main sequence, a stable period of nuclear fusion that can last billions of years, forming the life of a star. As the star exhausts its nuclear fuel, it expands into a red giant and ultimately shrinks down to a white dwarf, marking the twilight of its existence. The most massive stars go out with a bang, dying in spectacular supernova and leaving behind dense black holes. This death is not an end, but a new beginning. The remnants of these celestial explosions seed the cosmos with heavy elements, the building blocks of new stars, planets, and possibly life. In the grand tapestry of the universe, the life and death of stars is a cycle of cosmic renewal, seeding the cosmos with the building blocks of life itself.